In December 1972, the crew of Apollo 17 lifted off from the lunar surface. We haven't been back since. That 54-year hiatus is about to end. But NASA's objective has shifted entirely. The agency is no longer launching rockets to plant flags and leave footprints. The goal now is to build a permanent, self-sustaining human presence on the moon. To achieve that, engineers built the Orion spacecraft. And before stepping onto lunar dust, this capsule must survive a grueling 10-day test flight around the moon, known as Artemis II. Before any heavy infrastructure can be constructed on the surface, we have to definitively prove that our new hardware can keep a crew alive in the extreme hostility of deep space. This diagram compares the scale and thrust of the new Space Launch System, or SLS Block 1, side by side with the Apollo-era Saturn V. The SLS gains a massive power advantage through the addition of those twin 5-segment solid rocket boosters. At liftoff, the massive rocket combusts over 750,000 gallons of supercooled propellant, violently generating an incredible 8.8 million pounds of thrust. Riding on top of that controlled explosion are Commander Reed Wiseman, pilot Victor Glover, specialist Christina Koch, and Jeremy Hansen. They make up the most diverse crew ever assigned to a lunar mission, including the first woman, person of color, and international partner to leave low Earth orbit. They aren't along for a joyride. Look at this official NASA priority document. The primary objective requires the crew to actively test the systems designed to sustain them. They are test pilots, tasked with pushing Orion's life support systems to their absolute limits. Clearing the atmosphere in 8 minutes delivers the crew to their proving ground in deep space. Once Orion reaches Earth orbit, its survival relies entirely on the European Service Module, a 15-ton cylinder built by Airbus that functions as the spacecraft's engine room. This wireframe shows the module's architecture. It generates 11 kilowatts of power through 4 7-meter solar arrays and houses a 33-engine propulsion suite. For close-quarters maneuvering, Orion relies on 24 reaction control thrusters, firing in brief bursts to make microscopic adjustments in a vacuum. The crew puts those thrusters to work immediately in a highly delicate maneuver known as proximity operations, or Proxops. Pilot Victor Glover takes manual control of the spacecraft, flying Orion within 9 meters of the spent upper stage, using it as a floating target. NASA needs to know how the heavy capsule handles under human command, because future astronauts will execute this exact maneuver to dock with SpaceX's massive lunar lander. Future lunar landings rely on this specific manual interface. If Orion fails to handle precisely, NASA would be forced to reevaluate docking protocols for upcoming Starship missions. Once Proxops is complete, the main engine fires for the translunar injection burn. This pushes the crew far beyond the safety of Earth's protective magnetic field. Out here, they are fully exposed to the harshest biological threats in the solar system: high-energy galactic cosmic rays and volatile solar energetic particles. To study this threat, the mission carries the Avatar experiment, tracking how living bone marrow cells react to ionizing radiation in deep space. Avatar uses an organ-on-a-chip device containing actual bone marrow tissue donated by the crew. It tracks the real-time genetic damage occurring within those specific cells as the mission progresses. Orion carries these living tissue samples roughly 4,700 miles beyond the far side of the moon, pushing humans further into deep space than anyone has ever traveled. Quantifying the exact rate of this cellular decay is the only way NASA can accurately calculate the true physical cost of sending humans on a multi-month transit to Mars. This orbital map illustrates the mission's free return trajectory. Rather than entering lunar orbit, Orion uses the moon's gravity as a massive slingshot, naturally accelerating the capsule onto a direct path back toward Earth. After a 4-day coast, Orion slams into Earth's atmosphere, traveling at 25,000 miles per hour. This triggers the ultimate trial of the mission. The capsule's heat shield must withstand temperatures nearing 5,000 degrees Fahrenheit, enduring extreme friction, while communications are temporarily blocked by a wall of superheated plasma. A safe splashdown in the Pacific validates Orion as a flight-rated deep space vessel, capable of withstanding the extreme friction of a lunar return. That flight-proven data arrives just as NASA's overarching strategy takes a sharp turn. The agency recently canceled its long-planned orbital and lunar gateway station. This chart details the new financial reality. NASA is reallocating $30 billion into Project Ignition, a concentrated effort to construct a permanent habitat directly on the lunar surface by 2030. The mission data from Artemis II, the success of the manual Proxops, the thermal survival of the heat shield, and the deep space medical results from Avatar provides the direct technical evidence required to start building that surface infrastructure. The success of Artemis II establishes the technical foundation for a permanent base on the Moon, the first step in a much longer expansion toward